first talk is given by Florian Mutter on a capable distributed programming model.
So thank you for the introduction, Philip, and thank you all for attending my talk. So I'm Florian Mutter, and I'm here to talk about our vision for the future of distributed programming models, which is to incorporate the CAP theorem into their design. So let's assume for a moment that I want to implement an online presentation framework, sort of a Keynote 2.0 or a PowerPoint 2.0, which has two main pieces of functionality. The first one is that while the presenter is presenting the slides, a member of the audience can connect to a server and they're able to follow the slides while the presentation is going on their mobile devices, their laptops, etc. The second piece of functionality is that members of the audience can ask questions while the presentation is running. So you have this pop-up menu, you type in your question, the question is submitted to the server, and at the end of the presentation, the presenter goes through the questions and answers them. So a requirement for the slides part of the functionality is that all connected members of the audience should have a consistent view on which slide is the current one. You don't want half of the audience to think you're on slide 4, while you're actually on slide 10. So a way to implement this would be to maintain the state of the slideshow centralized on the server. As a member of the audience, you get the current slide by sending a request to the server, and as a presenter, you change the slide by invoking a set current request on the server as well. So a consequence of implementing the slideshow like this is that if a partition occurs, and a partition basically separates the network into disjoint subnetworks, so if such a partition occurs, then getting or setting the current slide might not be possible. So in distributed computing terminology, this is called a consistent partition tolerance system. So regarding the questions, the requirement is that members of the audience can always ask questions regardless of possible partitions. So even if you're currently disconnected to the server, you're able to ask a question, and then when the partition heals, when you reconnect to the server, the state is synchronized. So a way to implement this would be to replicate the questions from the server to all the clients. A consequence of this is that the state of the questions might temporarily diverge amongst clients. If I'm offline and I ask a question, then of course this question is not replicated to everyone in the audience. And so in distributed computing terminology, this is called an available and partition tolerance system. So what I've been explaining here, these trade-offs are actually a very famous theorem in distributed computing called the CAP theorem, which basically says that a partition tolerance system cannot be both available and consistent. So you have these three properties of a distributed system: partition tolerance, which I'll symbolize using the lightning strike; consistency, which I'll symbolize using the target; and availability, which I'll symbolize using the clock symbol. And so the theorem actually says that you have to pick two of these properties, and you can't have all. So basically the kinds of system we target are inherently prone to partitions. So we need to model these partitions. Our system needs to be partition tolerance, which leaves you with the choice between consistency and availability. So a common misconception about the CAP theorem is that it doesn't apply to systems as a whole, but the granularity is much more fine-grained, meaning that parts of the application state might need to be consistent. So for example, our slideshow, and part of the application state might need to be available, for example, the questions. Now when you look at distributed programming models and programming languages, they implicitly make this choice for the programmer, so this choice between consistency and availability, through the abstractions that they provide. So looking at languages such as ambient talk and E, they provide remote or far references, which allow you to easily implement consistent parts of your state, but they lack the abstractions to implement the available parts of your state. Vice versa, on the other side of the extreme, you have languages such as LASP, which relies on CRDTs, and so it's really easy to implement available state, but LASP lacks the abstractions to implement the consistent part of the state. And so what we bring forth in the paper, and what I'm here to present today, is a sort of a CAP-centric design towards distributed programming models. So we have this model called Captain, in which you implement your consistent state using consistent objects, and you implement your available state using available objects. So you have two object-oriented abstractions, which are first-class language constructs, distributed by nature, so you can send them around on the network, and it's up to the implementation of the model to guarantee the consistency and the availability of the objects. So we implemented this model in a prototype implementation called Captain.js, which is a TypeScript framework, so it's a full-stack TypeScript framework, meaning that you implement both your client and your server within Captain.js. and it explicitly targets mixed consistency web applications. So your client and your server are actually implemented as a collection of consistent and available objects. So I invite you all to go to the link at the top of the slide here. So in the paper, we motivate our work and we present our model using a collaborative grocery list application, which is sort of the hello world of consistency research. But I figured this is Onward, I might do something a bit more bold here. And so I went ahead and implemented the slides you're looking at now using Captain.js. So this Keynote 2.0 framework is actually running on the link at the top. So if you go to this link, you'll be able to follow the presentation. And you should all have the ability to ask questions. So there's this button here at the top. I can add a question. So I'll do the first one, and we can get this out of the way. So each member of the audience is able to ask 2 questions, and you're also able to upvote twice a particular question. All right. So what are sort of the concerns as a programmer when I start to implement such a framework, or what does Captain provide for me? So basically, there's a clear API. So how do I implement my available state? How do I implement my consistent state from a language perspective? These objects are inherently distributed, so they need message passing semantics. How does the Captain.js runtime guarantee availability and consistency? And then lastly, these objects are part of a bigger ecosystem. In this case, it's the web. So how do these objects interact with their environments, and how do they interact with each other? So starting off with the consistent part of our application, so in this case, it's the slideshow. Captain.js provides you a class, consistent, so we extend this class in order to implement our slideshow. So there's 2 pieces of state. There's the current slide, which is a number, and then we have an array of HTML elements, which are the actual slides. And so this current slide here, it's basically an index into that array. So there's 2 methods. There's the next slide method, which increments this index, which can only be invoked by my phone here or my laptop, in order to avoid having you change the slide whenever you feel like it. And then there's the get slide method, which can be invoked by any of you to request a current slide from the server. So as a client or as a server, how do I interact with this consistent object? So on the server side basically only instantiates an object from the slideshow class, and it provides one method, register, which returns the slideshow. So this register method will be invoked by a connecting client. On the client side, assuming that this reference here, server, is a reference on which the client can invoke remote methods. So the client invokes the register method, which returns the promise. So this .then syntax is JavaScript syntax for promises. So this promise is going to resolve with the slideshow. And from this point on, the client is able to start interacting with the slideshow. So remember, the goal of the slideshow is to be consistent. So the trade-off here is that it might not be available. So for instance, invoking slides.getSlide here returns a promise which might resolve with the current slide. And I say might because if you invoke this method while you're offline, well, the promise won't resolve. And another way to look at this is that the Captain.js framework will only resolve the promise if it can guarantee the consistency of this method invocation there. So what is the message passing semantics for consistent objects? Well, they're disseminated across the network by file reference, which is terminology stemming from E and ambient talk. The idea being that when the client invokes the register method on the server, what the server returns is a file reference to the slideshow. And a file reference is implemented as a proxy. So when I say proxy, I don't mean in the networking sense, but proxy in the meta-programming sense. So basically, what the server returns is a hollow shell of an object, which points back to the original object living on the server. How is this used to implement consistency, or more specifically, sequential consistency? So let's say that we're on the client here, and we have an object, a regular object, invoking a method on a file reference. So we invoke next slide, for instance. So what is returned is a promise, as I said before. But in the background, Captain.js is going to send an invoke message to the server. This invoke message contains the name of the method invoked and the arguments used during the invocation. Upon receiving this message, the server is going to invoke the method on the original consistent object and return the return value in a resolve message, which is going to resolve our promise return at timestamp 2. So regarding the available, so what has to be available in our application here is the ability to ask questions. So there's 2 pieces of available state. implemented by extending the available class permitted by captain.js. So we have the question list, which is going to contain all the questions. So there's this hash map here from string to question object, string being the ID of the question. And it provides one method, new question, which takes a question object and sets it in the hash map. And so you'll notice this add mutating annotation here. So the idea behind an available is that you can always read the state, set the state, invoke a method, but the state might diverge amongst clients. And so by using this add mutating annotation here, the programmer informs our runtime, hey, whenever I invoke this method, I might make the state diverge amongst clients in the network. And so whenever you can, you should try to synchronize all the states of the question list. So within the question list, we have questions, which are also available objects. They contain text, the actual question, the number of upvotes, and an ID. And the question object provides one mutating method to increment the upvote of a particular question. So there's two levels of availability here. You have your question list, which is available, always able to add a new question. And then within this available question list, you have questions themselves, which are available. So it's always possible to increment the votes on a particular question. So as a client or as a server, how do you interact with an available object? So I omitted the server-side code for the consistent part of the application for the sake of brevity here, but the idea is more or less the same. The server instantiates an object from the question list class, and the register method returns an instance, returns the question list. So on the client, so we have the server reference here, which allows us to do RMI. So we register on the server, we get back a promise which resolves with the question list. And at this point on, our client is able to interact with the question list, which happens synchronously. So remember, availables are always available. You should always be able to invoke a method. And so for instance here, questions.questions is going to return a hash map contained in the question list, synchronously, locally. So there's two kinds of callbacks you can register on an available. There's the onTentative callback, which is invoked whenever a mutating method finishes locally. And then there's the onCommit callbacks, which will be triggered whenever the state updates globally. So if one of you asks a question, the onCommit callback will be triggered for all other members of the audience. So the message passing semantics are that available objects are disseminated across the network by replica, meaning that when a client registers to the server returns a replica of the question list, a replica being a deep copy, so both states as well as methods. How is this used to guarantee availability and non-strong eventual consistency? So underlying captain.js is an implementation of the global sequence protocol, which actually provides more than non-strong eventual consistency, but I'm not going to go into the fine details. I'm going to give you a high-level overview of how it conceptually works. So on the client and on the server, you maintain an operation log per available object, and this operation log is going to contain all the method invocations on a particular available object. So if we have a regular object that invokes a method on an available object, the result is immediately returned. Remember, this happens locally, but the invocation is logged in the operation log. In the background, captain.js is going to send this new op message here to the server. Upon receiving this message, the server adds the operation to its operation log, resets the state of the available object to the initial state, and reperforms all operations in the log. After which, it sends the new log to all replicas of that particular available object. So if you ask a question using my tool, it's sent to the server reperforms all the question additions, if you want, and sends out the new log to every one of you. So how do these objects interact with their environment, more specifically the lexical scope? Well, they don't. You can't access the lexical scope from within a consistent or an available object, and this might seem a bit harsh, but it's actually common practice in distributed computing. So you have isolates in ambient talk, isols in Pony. There's this technique called spores, which is different but resembles the ID we're presenting here. And the reason is that, for instance, in this class foo here, I access the variable x, but given that these objects are distributed across the network, I can't rely on the fact that the entire lexical scope will be copied together with the object. What is possible, though, is the code on the right. So during construction time, it's possible for an object to copy over lexical information into its namespace. So the x here is copied into foo's namespace. So then the question remains, how do availables and consistents interact with each other? And again, the short answer here is that they don't. There's a clear separation of worlds. There's the available world and the consistent world. And to give you an idea of why this is, I'm going to quickly repeat the sort of the mantra behind availables and consistents. So the idea is that an available and its replicas only expose possibly inconsistent available values. Meaning that if I invoke a method on an available, or if I read the state, what I expect back is an available value. And conversely, a consistent and its file references only expose possibly unavailable consistent values. If I read the state or if I invoke a method, I expect to have a consistent value back. And so what Captain.js disallows at runtime is, for instance, for an available to return a consistent object, or for an available to have a consistent object at one of its instance variables. Conversely, the same holds, the inverse holds for consistent objects. So this is of course very restricting from a programmer's perspective. So what we do provide are two methods which allow you to have some interaction between both, namely thaw and freeze. And the idea is that thaw allows you to turn a consistent object into an available object, and freeze allows you to turn an available object back into a consistent object. And how this works is, for instance, in the case of thaw, you take a consistent, you take a snapshot copy of the state, and the state is returned in an available form. So to give you an idea of how this works in practice, I'm going to give you a concrete example. So we implemented the slideshow using a consistent. What that means is that if I lose connection to the server, I'm unable to change my slides, which is rather annoying. And so I have this lightning strike button here at the top. And this allows me to optimistically go into offline mode. So before I lose connection, I can press the button. And I'll turn off my Wi-Fi in the meanwhile. So what happened here is that I requested the server to thaw the slideshow, which is consistent, and return me the available version of the slideshow. So I'm now able to change my slides. And of course, this is not hyper cost on your devices, given that I'm offline. So if I reconnect to the Wi-Fi and reconnect to the server, I'm able to, sorry for this is Chrome. Yep. So I'm able to refreeze, at which point we're consistent again. So what I did here by repressing the button is taking the available version of the slideshow, send it to the server freezes this back into a consistent, and we're now all consistent again on the same slide. So there's a clear functional trade-off between availables and consistents. If you want offline availability, implement your state as an available. If you need it to be consistent, implement it as a consistent. But there's also a clear performance difference between both. And to highlight this, I'll be first introducing two performance measures. The first one is time to consistency. So it's the time required for a write by one client to be visible to all other clients. So if I have a client here, which mutates the states of a consistent or an available, how long does it take for this mutation to be visible to all other clients? That's the measure. The second measure is the time to local change. So the time required for a write by one client to be visible to the same client. So let's say I have a client called C1 here. C1 mutates the state of a consistent or an available. How long does it take for that mutation to be visible to C1 itself? So what I could have done is show you static benchmarks, which I ran, the results of static benchmarks that I ran a couple of weeks ago. But I figured this is Onwards, so we might do something quick or bold. I'm not going to call them benchmarks because I don't want to scare you off, but I'm going to use the 22 of you that are connected to my server in order to run some experiments to showcase you the difference between consistents and availables. So I have this button here at the top, this timer button. When I press the button, I'm going to send you a consistent and available object on which you will perform 10 operations, and as the data gets back into my server, we'll see the results flowing in. So what we see is what one would expect, namely that the average time to local change for availables is, you can't see it, the results are there, but it's instantaneous. And this makes sense because invoking a method on an available happens locally. And so what we're basically measuring here is how long does it take for JavaScript to perform a method invocation on an object, which is near instantaneous. Especially compared to consistents. So when you invoke the method on the consistent objects that I sent you, this is basically a message being sent to my server in Belgium, which performs the operation and sends back the result here in Boston. So what we're seeing here is the round trip time for a message to Belgium and back to Boston, together with some overhead due to midlife device, etc. Regarding the time to consistency, this is much higher for availables than consistents. So whenever you perform an operation on an available, this is sent to my server. My server reperforms all the operations and sends back the entire log to all of you. You then need to reperform this log of operations, and only then is the state consistent. If you compare this to a consistent object, this only takes one round-trip message. Actually, not even a round trip, just one message. You perform an operation on a consistent, this is sent to my server, it performs the operation, and the state is technically consistent because the only state that is maintained for a consistent is maintained on the server. So to conclude, when we look at current programming, distributed programming models, they implicitly make the choice for the programmer which kind of state they provide abstractions for. There are languages such as E or ambient talk, which through their remote and far references make it really easy to implement consistent and partition-tolerant systems or states. And then there's languages such as LASP, which provide the inverse. So using their CRDTs, it's really easy to implement available states, but they lack the abstractions to implement consistent states. And so the takeaway message of my talk here, and the main idea of the paper, is that future distributed programming models should make it explicit to the programmer what kind of state they're implementing. And so Captain.js provides you two ways of doing this. So an API to implement available state, available class, and an API to implement consistent state. Moreover, we provide clear message passing semantics, given that these objects are inherently distributed. Captain.js provides you the runtime guarantees for availability and consistency. So as a programmer, I'm freed from actually having to implement this myself. And there's clear interaction rules for availables and consistents and their environments, and for availables and consistents amongst themselves. So thank you for your attention. If you're interested in the slides, you should now all have the availability to thaw the slides. So there's this lightning button which should be available on all your devices. If you're on a laptop, you can use your keys. If you're on a smartphone, you can just swipe. Or you can look at the source code of the slides. Captain.js is on GitHub, and it's also an NPM package. And you can find me on Twitter using the following. Thank you.